All right. Maybe we should start. So welcome everyone to a new edition of the IEC research seminars today on Tuesday. It's my pleasure to have Alejandra visiting us from Durham. Alejandra, maybe you already know her. She's been visiting us for 2 weeks thanks to the XCAL Twin project. But as a matter of fact, I used this as an opportunity to organize also a workshop seminar by her within the UNDARK framework, because she's working on things related to dark matter and with n-body simulation. I thought it was a very interesting aspect to cover by her. So Alejandra, she's a postdoc now at Durham University, but she did her PhD and her master's with Miguel Ángel Sánchez Conde in the Universidad Autónoma de Madrid. And before that, she did the degree in the Complutense, and she started working also with gamma ray astronomy. And actually, her first paper was on projections on gamma ray searches of dark matter with CTA. Okay, without further ado, Alejandra, thanks for visiting and for accepting giving a seminar. The floor is yours.
Thank you very much, Jorge, for the very nice introduction. Can you hear me well like this? Okay, great. Well, then I don't have to introduce myself because I have been very well introduced. So I'm going to start talking about dark matter, which is what I work on. Well, if you have been here on Thursday, from Miguel's seminar, some information is going to be kind of shared. So it's a bit of repetition, but I think it's also good to keep things in mind. So yeah, there's a lot of observational evidence of dark matter at galactic scales, extragalactic scales, cosmological scales. All of those evidence are astrophysical. We have the rotation curves, weak lensing, the velocity dispersion, the clusters, the movement in clusters, the CMB, etc. But we still don't know what dark matter is. There's no particle in the standard model that can explain all of these observations. And we have this lambda CDM model, which is lambda for dark energy, which explains this accelerated expansion in the universe, and the CDM called dark matter, because we believe that dark matter should be cold, stable at cosmological scale, electromagnetically neutral, so it doesn't interact with photons, and also non-baryonic. It's not contained in the standard model. And we believe that there's more or less kind of 25% of dark matter, maybe 27, something like this, and like 70% of dark energy and less than 5% of ordinary matter. We believe in this cold dark matter, the structure formation is thought to be bottom up. So this means that we start having very small structures. They merge and they become larger and larger. And then when these structures be realized, we call them dark matter halos. And then they have mergers and so on. And there are halos within halos. And that's when we have a halo within another halo, we call it subhalo. And we also have this large-scale structure formed by all of these filaments and voids and so on, which we can see here. This is an evolution of how the universe would work with time in the dark matter components. And this large-scale structure is studied especially by, well, we have several ways. One of them is the large surveys using ground and space telescopes. We also have some analytical approaches and cosmological simulations, which are the best tools, especially in the nonlinear regime. And this, for the small scales, the simulations are very important, and also the small scales are very relevant themselves to disentangle if we are really in a cold dark matter world, or the dark matter is more warm or self-interacting, or it's an alternative mode. And we have different kinds of cosmological simulations. According to the matter that they have, we have two kinds. So we have dark matter only simulations, only dark matter, that's just what it says. These are collisionless. And we also have the hydrodynamical simulations, which include the baryonic feedback, the dynamics, the gas, the stars, etc. And then we can study the impact of baryons in the dark matter and the impact of dark matter on baryons. And according to size, we have two different classifications as well. So we have the large volume, which study the large-scale structure. They can provide statistical samples of galaxies, and the zooming, which provide details of particular galaxies and objects, and they make possible to study the substructure of the halos. And well, this is okay. This is how the dark matter in a galaxy like the Milky Way would look like. So we have a smooth dark matter halo, which is this. So the light corresponds to density of dark matter. So we have this whole dark matter halo. We have it like this. We here have inside the luminous matter, the disk, the stars, and so on. And these small clumps that we see, we have some bigger clumps and smaller clumps. The bigger ones are expected to host what we see in the sky as dwarf galaxies. And we also have a lot of smaller ones, which are what we call dark satellites because they don't have any baryons at all inside. So they are so small that they cannot hold the baryons. And they would be only dark matter formed. So it's really hard to find them with with like optical wavelengths or radio or etc. Yeah, as I said, we still don't know what this dark matter is. There's a lot of possible candidates that could be this dark matter. And in particular, we focus here on the weakly interacting massive particles, which are some of the cold dark matter candidates, one of the most preferred ones. And we have different ways to look for them. One of them is direct production, which is this one. So we have two standard model particles which collide, and maybe they form a some dark matter particles. We also have direct detection. So maybe one standard model particle faces a dark matter particle, and then there's some scattering of the standard model particle, and we can study this effect. And also we have indirect detection, which is the one I'm going to focus in this talk. And it's two dark matter particles annihilating and producing standard model particles. And there are different possible annihilation products. We have maybe neutrinos. We have also antimatter and gamma rays, which are the most energetic photons in the universe. And in particular, we call the gamma rays the golden channel because the neutrinos are very difficult to detect, and the antimatter can be deflected by magnetic fields, and it loses energy because of this. But the gamma rays travel following straight lines, and they are not attenuated, so it's easier to detect them. And the energy of the annihilation products depends on the mass of the dark matter particle and its order GeV, TeV for this cold dark matter. We have that the gamma ray flux is computed in this way. There are two factors, the particle physics factor. It depends on the mass of the dark matter particle and the cross-section, and the J factor, which is the astrophysical factor, and depends on the dark matter density profile squared. And now we are going to see the master equation for this flux. So this is the same, but more specific. This is the particle physics factor. This is the mass of the dark matter. This is the cross-section. This is the photon flux is here, which depends on the annihilation channel we are considering. And here, this is the astrophysical factor, which is basically, as I said, the integration of the dark matter density profile squared along the line of sight. And in particular, I focus on these dark satellites that I was talking about. And this is because they are very high dark matter dominated. And then, well, both dwarfs and dark satellites are very good targets, but I'm going to focus more on the dark satellites, as you will see later. And we are going to have a lot of them inside our own galaxy, according to this cold dark matter model. Also, this clumpy distribution inside the halos would enhance the annihilation signal of the halos. And well, in part, the cosmological simulations are very useful, as I said, to elucidate the abundance of the and distribution of this substructure. And yeah, since simulations are really very nice, I wanted to just have a short film of what a simulation looks like, so you can see if you haven't. I guess you have, but just in case. So in this case, you are seeing how a single massive galaxy is forming in the TNG cosmic simulation. So you can see in this case, yeah, you can see how the time is evolving, and also how the mass is evolving and how it looks like in the end. And yeah, okay, so I was talking about how powerful are simulations, but they are also limited. So they have a numerical and particle resolution, and then you cannot have any structures which have masses several times the particle mass of the simulation. And also they have some artificial disruption, etc. And we have different procedures to overcome this issue. One of them is repopulating a cosmological simulation. So according to our predictions and the simulation itself, we can generate subhalos below the resolution limit of this original simulation. And other one is studying the evolution of a single object, which is orbiting a host, which is simulated in an analytical way instead of with particles. And I'm going to explain both of them in more detail now. So the first one is the repopulation. It's useful because we still don't know how the basic properties of subhalos are, the abundance of them, the distribution structure. We have some predictions, but it's still not clear. And then the goal of this project is to characterize and repopulate a high-resolution swimming cosmological simulation. And this is very useful because then we can study the relevance of these very small subhalos for dark matter searches, and reaching these scales that are not resolved in the parent simulation. And we also are going to obtain properties which are very relevant for the gamma ray searches, which are going to be the J factors and also angular sizes. We are doing this in two different ways. One of them is using what we call the subhalo mass, which is not virial mass because subhalos don't have a mass really well defined like a virial radius and so on, because they are stripped, as we will see later. So we have this parameter called subhalo mass. It's kind of a tidal mass. And also we are going to use another parameter, which is the circular velocity, the peak of it, which is called the maximum circular velocity. This is so the velocity of the dark matter particles inside a halo or a subhalo follow a circular velocity curve, and the peak of this curve is called Vmax, maximum circular velocity. And in particular, we are using this simulation called Via Lactea 2 because it has still a very good resolution, and the data is public at Redshift 0. More details about the simulation. So it's a Milky Way size halo. We have subhalos down to like 10 to the 4 solar masses in this simulation. So we have a lot of subhalos to play with to extrapolate the relevant quantities and so on. As I said, the data was public. It's n-body, which is not as good as we would like because it's more realistic when it has baryons, but it's useful for our purposes. It's collisionless because of this. And yep, so the thing is that it's a bit old, so the cosmology is not Planck, it's WMAC 3, but it's fine because these parameters in these parameters measured by this WMAP 3 are conservative, so we are not predicting a lot of subhalos that we don't want to. So we are predicting a number of subhalos which are not exceeding what are our current expectations. And so this is how we characterize the population of subhalos using the mass. We study the subhalo mass function. This, according to press sector, it's going to follow a power law, but it's not resolved below this point, more or less, which is 5 times 10 to the 6 solar masses. So we are extrapolating below that. And this is the parameters that we found for the fit. And we also study the radial distribution of subhalos. So we have more subhalos outside and less subhalos inside. And we have also a function for this distribution. And we also need another parameter, which is called the concentration, which is basically how the internal structure of the subhalo. This was studied already by Molinet et al. 2017. And the interesting fact is that for subhalos, it depends not only on the mass, but also on the distance to the galactic center. And we have done the same for the maximum circular velocities. So we have the subhalo velocity function. In this case, this is 4 kilometers per second, where it starts to drop, and then we extrapolate below. This is the best fit parameters. And in this case, the radial distribution for this completeness part is also a bit different. So we are using a different function for this. It peaks here instead of going just up. And we have these best fit parameters. And the same for the concentrations. The same paper has also the expression in this case. So we have seen that this simulation Via Láctea 2 is complete above these values for mass and velocity. And now we are going to do the repopulation. So what are we doing? We are calculating the expected number of subhalos using either the subhalo mass function or the subhalo velocity function. Then we are assigning a mass or velocity to each one of them. We assign a distance to the galactic center to each one of them, concentration too, using the mass and the distance. And then with all of this, we can calculate the annihilation J factors by placing the Earth at the solar galactocentric distance. And we can also calculate the angular sizes of these objects. So we have done this in two different ways. When the masses or velocities are not really, really low, we can repopulate the whole galaxy, the whole Milky Way. So we have done this for masses down to 10 to the 3 solar masses, and for velocities down to 0.5 kilometers per second. This is what we call the sets A, AM, and AB. And when we want to go even below that, because it's really computationally expensive to simulate such an amount of objects, then we only repopulate a shell around the solar galactocentric radius, because in reality, we are only interested in the area around the sun, the Earth, let's say. But this is easier than just doing this circle here. So we do these shells, and doing this, we can go down to, for masses, we have gone down to 0.1 solar masses, and for velocities to 0.05 kilometers per second. We have also done some checks to see that the repopulations work as we expect. So for the mass case, we can see, so this is the set AM, and we see how the repopulation works well, down to 1,000 solar masses. And for the radial distributions, we have both here for sets AM and AB, and these symbols are the repopulated structure, and we see that they follow the distributions that we wanted. And again, so we are going to now calculate these J factors. This is what we are going to focus on now. So for masses, we get this expression, which takes into account the distance of the subhalo to the Earth, the mass of the subhalo, the concentration, well, also some kind of like the size of the subhalo. And then with all of this, we can calculate these J factors. So if we just use the parent simulation, we get this result. But if we go to the repopulation, we get this. So the color represents the mass, and we can see that this black color is the lowest masses, and we find that some of these subhalos, the brightest ones, so the ones with larger J factor, are ones which are very low massive, which is very relevant. So this means that subhalos, we could have in our galaxy very small subhalos very close to the Earth, and maybe we could detect them. And then if we do this a lot of times, in particular 1,000 times, and we just plot the 100 brightest subhalos of each one, then we can find this. So the repopulation is more relevant here. We are combining now both sets, the A and B. And again, we can see that many of these brightest subhalos are very low massive, like less than 10 solar masses. And for Vmax, we do the same. This is the expression in this case. So we have here the concentration, Vmax, and the distance to the Earth as well. And again, we find that there are some of the most bright subhalos which are which have very low Vmax. And here we are just plotting the most brilliant subhalo across these 1,000 repopulations. On left-hand side with mass, right-hand side with Vmax. And yeah, it's basically the same. Sometimes we have this brightest subhalo, which is a very small one and very close to us. And we also find that J factors calculated via Vmax are usually larger. We are so this, if we use this like the similar expressions for both, this should not happen, but there are different reasons for this. I'm going to talk about this just in a moment. And also we computed the angular sizes. This is the expression. And what we find, this is the mass case, the repopulation with mass. We find that the brightest subhalos appear as extended in the sky. So the thing is that, well, we have studied the impact of these very low mass subhalos, very low mass, low velocity for dark matter and indirect searches. And we have characterized this Via Láctea 2 simulation and repopulated it down to 0.1 solar masses and 0.5 kilometers per second in each case. We have found that these dark satellites can appear as bright as dwarfs, and sometimes very, very low mass or velocity subhalos may still be relevant for dark matter searches. And as I said, sometimes in general, the subhalos calculated, the J factors calculated with Vmax are sometimes larger, maybe even 1 order of magnitude larger. But we have seen that, for instance, the subhalo radial distribution of Vmax was different. It had a peak, while the one for masses just went to, it was, the distribution went to larger distances. Also, the integration of the J factor is not done until the same size of the halo. So there are different reasons that could account for this discrepancy. And yeah, as I said also, the brightest subhalos in these simulations are expected to be extended. This has different applications. For instance, we can set dark matter constraints if we compare these results of the simulation with the number of unidentified gamma ray sources in the Fermi-Lat catalogs. This was done already in some works that I collaborated with Javier Coronado Blázquez, Miguel Sánchez Conde et al. And also, also to extended subhalos. And we also studied the sensitivity of CTA. This was prospects to dark subhalos in this other work. This is also useful to compute more precisely the boost factor. Yeah, so on. So in this particular case, we are setting constraints to the cross-section, the annihilation cross-section of dark matter using this work. And also we are now studying the impact of baryons in all of this. We are using now the simulation Auriga, which is hydrodynamical, and we have data from 6 Milky Way size halos with dark matter only counterparts, so we can compare between them. And in this case, we are extrapolating the subhalo characterization down to 0.1 kilometers per second. Here we can see how we have this resolution limit, so we want to extrapolate down. And so yeah, in this case, we are plotting the brightest subhalo in a lot of, in this case, I think it's 500 simulations. And in particular, we see that in hydro, we find that the J factors are lower compared to dark matter only. But Also, we lose part of this small stuff, but you have to take into account that this is still preliminary, and we are also, sorry. So we have two different approaches here. We are going to use two different radial distributions. This one is according to the simulation and is what we call fragile. And we have another one, which is going to be called resilient. So we expect to have more subhalos in the inner parts that the simulation is artificially destroying. So the results are changing. So you will have to stay tuned to see the final results of this. And again, we can see how the baryons are shifting the dark matter annihilation cross-section according to these results up. So the constraints are less stringent. And we also have studied all other halos, other hosts beyond the Milky Way, and other models of dark matter, alternative to cold dark matter. In particular, beyond the Milky Way, we have used the U2, Shin-2, and Phi 1496 simulations, which it's a whole suite of simulations. So the Phi are more high resolution and the U2 are more large volume. So here we can study host masses spanning many orders of magnitude. And we have also studied interacting dark matter, which is a possible and natural deviation from cold dark matter, which is interactions between the dark matter and photons or neutrinos. And this implies a suppression in small scale structure, but we still can have WIMPs. So for U2, Sin2, and Phi, we can find, well, in this case, I was characterizing also the subhalo mass function and radial distributions. In this case, there's no repopulation, it's just the characterization of the simulation. And well, here we have the mass and velocity functions. This is the Sin2 simulation, the intermediate one for different host masses, from 10 to the 8.8 to 10 to the 3.8. This is how the three of them combine here. But this is only for Milky Way-like hosts, and this is the velocity, the subhalo velocity function. In this case, we were using a bit more refined expression rather than the power law, which is defined in this paper, Rodriguez Puebla et al. In 2016. And these are the parameters we find for the fit. And for the interacting dark matter, we have this. So we also have the cold dark matter counterpart. And we have both local groups, which are more like zooming, and boxes. And we can see the difference between the IDM, which are the points, which are always below, the CDM, which are the triangles. And this is, in this case, we are using the power law, and these are the fits. We also studied the time evolution of these subhalo mass functions and velocity functions. We had a lot of amount of data in this suite, so it was able to study these functions for different redshifts down to redshift 4. And the power law indices agree very well with the expectations. In general, like 1.9 or so for the mass, for the subhalo mass function. And so this is the second part. So I talked about the characterization or population of different simulations. And now I'm going to talk about studying a single subhalo orbiting around a host. So there's still an open debate in the literature, because we are not sure if these small subhalos are going to survive the tidal forces that experience because they are inside a host halo, or they are going to be completely disrupted after orbiting. So there's one group of people who believe that all of this is this disruption in simulations is due to numerical resolutions, artificial effects, and so on, and there should be some cast which always survive, but others think that there are physical tidal forces within the host that are able to completely disrupt the subhalo. So the goal of this project is study this subhalo survival using numerical simulations and the impact of this possible survival of subhalos for gamma researches. In this case, we are using high-resolution numerical simulations, which follow the evolution of a single object, and we will see that it's going to lose mass mainly in the pericenter. Well, in this case, the orbit is circular, so there's no pericenter, but in the cases I'm going to study, we have more elliptical orbits, and we will see this. The code we are using, Dash, was performed by, well, you can see here an example of this evolution of the subhalo, was performed by Aguirre-Santaella. It follows the evolution of this subhalo with, which is an n-body system with a lot of particles orbiting the host, which is simulated analytically from the accretion redshift to present time. And then we have a lot of free parameters that we can choose. The number of particles, often in length, the initial subhalo mass and concentration, the orbital parameters, which are the circularity. So we have, so circularity 1 means circular, circularity 0 would mean completely radial. And the orbital energy basically means like the mean distance to the host. So a larger orbital energy means that the subhalo is farther away from the host in general. And also the accretion redshift is another free parameter. And for this work, we improved the original Dash code that we had, and we include the baryonic components as mass distributions. So we have the stellar disk and gas disk as Miyamoto-Nagai disk. They are a combination of them, and also a bulge, which is simulated with a Henquist potential. And both the dark matter potential and the baryonic potentials are evolving with time. So this is what we have when we look at the bound mass fraction of a subhalo. So these are the parameters we have chosen in this case, and the concentration is 10. This is like an average orbital energy, not too low, not too large. This is quite elliptical, this eta value, the circularity, accretion redshift 2, more or less standard, and this subhalo mass is 1 million solar masses. This is the orbit of the subhalo, and we can see that when the subhalo approaches the pericenter, we have a leap in this parameter, which is the bound mass fraction, which is the fraction of mass that remains bound to the subhalo at a particular time. This is basically time, so this is present time, this is the initial, so the redshift 2 is this. And we have seen that the subhalo has lost like 90% of the initial mass after several orbits. And yeah, the large mass loss occurs in the pericenter. Also, we have two convergence criteria. We have to take into account the maximum of the two. One of them depends on the softening length, and the other on the number of particles that we are using. In this case, we are way above the convergence line, so we are safe. We can trust the simulation perfectly. And we have also studied how this bound mass fraction changes when we change one parameter and leave all the others fixed. If we change the concentration, when we increase the concentration, the subhalo is going to survive more. When the orbit is more circular, the subhalo is going to survive more. When the subhalo is farther away from the host, it's going to survive more. All of this is really expected. And when the subhalo is accreted earlier, the subhalo is going to lose more mass than when it's accreted later. And when we include baryons to this host potential, we also find that the amount of mass lost by the subhalo is larger. And especially in the pericenter, we see how this mass distribution affects the subhalo a lot. So when we use more elliptical orbits, we find that the change is really significant. For instance, in this case, this green line, we have a larger concentration than the others, but it's really more elliptical than the others. So when we only use dark matter, it's the one that has a larger bound mass fraction in the end. But when we include baryons, it's the one that has the lower bound mass fraction in the end. This is just how the mass of each component of the host is evolving. This one is the dark matter. This is all the galaxy components combined. And so blue stellar, the red dot is the gas, and this green is the bulge. And if we want to study what happens when we change two different parameters at the same time, we can have this kind of plots. In this case, we are changing the concentration and the circularity, leaving all of the other parameters fixed. This is only dark matter, and this is including baryons. This is the bound mass fraction at present time. And well, we are using like standard values that we expect that subhalos would have in the Milky Way. We also have this blank area, which means that we have not reached convergence. So the line, the bound mass fraction, has dropped below this convergence line that I was showing you before. And in particular, we can see when we use the ratio between both bound mass fractions, that the circularity becomes really important when we include the baryons. But also when, well, in general, as we expected, if either the concentration is larger or the circularity is larger, the bound mass fraction is larger. And again, this is also important because we want to study the annihilation flux. And for this, we need the density profiles of the subhalos. So the dark matter density profile, the initial one that we are assuming is an NFW, which has a cusp in the center. But when we use these simulations, we see how the subhalo density profile, well, we see both the two things. One of them is that the density profile gets truncated when the mass loss takes place. This is really expected. So if this is the initial one at accretion redshift, then at another, so this is redshift 2, so this is redshift 0.51, we can see how it has been tidal stripped in the outer part. But we also find that the innermost part, so for instance, for this red line with 10 to the 2 to the 18 particles, the innermost part is also not obtained accurately, so the cusp is like being removed. But when we increase the resolution, we recover the cusp. But the thing is that we don't want to use this very high resolution for a lot of different simulations. So what we do in this case is using a semi-analytical approach that recovers this cusp. So this is this red dashed thick line. It recovers the cusp that we should find, and that we find when we have a larger number of particles. So here, with this dark matter profile, we can study the annihilation luminosity during the integration, the integral of this density squared. So here we are I'm showing the ratio between the initial luminosity and the one at a given time, from accretion redshift, which is 1, to present time. So again, it's very similar to the bound mass fraction. For different concentration, well, the main losses occur at the pericenter. For different concentrations, we find different behaviors. Less concentrated subhalos lose more luminosity. Also, when we include baryons, the same behavior as with the bound mass fraction. And in particular, we expect some subhalos, when we include baryons especially, to lose 99% of the initial annihilation luminosity. But they are still there. And for when we change both the concentration and the circularity, if we don't include baryons, we see that the concentration is very important. So the circularity is not so relevant. But when we include baryons, we find how this circularity becomes really important again. We also can see here the same when we compute the ratio between the two, that this is very dark in this part. And again, we have some non-convergence in this corner. And so we have seen that we have a lot of different initial parameters, and we wanted to see if we can find a relation for many of them or all of them, if we can. we started to look at the pericenter, how the bound mass fraction is at the pericenter. And then if we don't change the concentration, so the concentration in all of these runs is the same, we find that for dark matter only, there's a single power law that explains more or less everything with some scatter. When we include the baryonic mass distributions, we find another one. But yeah, so we are using different accretion redshift and different orbital parameters. Okay, thank you. And more or less, we find the same, but we wanted to go a step further. Before that, so for the luminosity, we also find some relations, but it's a bit more complicated. But we also can find that when the pericenter is in the solar vicinity, subhalos lose, like without baryons, like 60 to 90% of the initial luminosity, with baryons up to 99%, as I said before. Okay, I have to rush a bit. And also, so yeah, if we want to go a step further and have a relation for everything, we can use this parameter, which is basically how the tidal field, how strong the tidal field of the host is at the pericenter. And using this parameter, and also this is not exactly the bound mass fraction, it's a bit different. So then we can take into account different concentrations, and the relation is the same for dark matter only runs and for runs including the baryonic mass distributions. So yeah, the most important conclusion for this part is that most subhalos don't disrupt even after losing more than 99% of the initial mass. And I say most because for some cases, as I said before, we cannot reach convergence, so we cannot say anything. But for all of the subhalos that are converged are still there. And yeah, we have used between 10 to the 5, 10 to the 7 particles in this work for the subhalos. And also including baryons is really, really important. We have seen how the mass and the luminosities are more depleted. And okay, so we are following up on this using the same work, the same code, this dash code, to study the evolution of Vmax and the concentration. And so this is how the circular velocity changes with time. The yellow is the initial one, and this purple is the one at present time. So we can see how Vmax and Rmax both decrease with time. But the thing is that Rmax decreases more than Vmax. So using this formula, we can see how the concentration, this concentration increases with time. And we are also studying the tidal tracks of subhalos. This is, so basically we expect that all of the subhalos behave in the same way when orbiting, like the relation between the bound mass fraction and Vmax, also the relation between Vmax and Rmax at the apocenter is going to be the same for different initial configurations. And we are finding this, we are also comparing with other works that have done the same. We more or less coincide with Peñarrubia et al. 2010, not with a newer work that has been done by Shaolong Du and Andrew Benson. Let's see. And we also study the concentrations with Vmax, but this is a preliminary work. And now I'm also going to more large-scale structure using the colibri simulations. They are hydrodynamical, so we have both thermal and, well, we have some of them with thermal AGN feedback and some of them with hybrid, so there's both thermal feedback and jets. And they also have the dark matter only counterparts. They have different resolutions. The higher resolution is 10 to the 5, around 10 to the 5 solar masses. The lower is 10 to the 7 solar masses in particle mass. And we are going to make predictions for gamma ray annihilation emission from both satellites, I mean subhalos, and central, which are basically the host halos, in halos of a very large range of masses. And we are starting this work now. We are also, we have to take into account that So the thing is that we don't know if the baryons are shaping the density profile so that they have a core in the center or not. If they have a core, the annihilation luminosity is going to be much lower than if the profile has an NFW. And yeah, we are still studying this, or maybe there's even enhanced emission because of the adiabatic compression of the halo due to the baryons. So this is still work in progress. Yeah, so just to finish, to wrap up, unfortunately, dark matter has not been detected yet. We think that we can study the nature of dark matter using these cosmological simulations and numerical simulations. And we believe that these substructure are very good targets for dark matter searches, but we still don't know very well their structure and their abundance and so on, especially at the smaller scales. And having an accurate knowledge of this abundance and structure of subhalos is very important to disentangle if we live in a cold dark matter world or in a different world. Both dwarfs and dark satellites are very good candidates to look for dark matter. And in particular, we find that small subhalos can be relevant for these dark matter searches, so it would be interesting to look for them. And we also expect that these low mass or low velocity subhalos are going to survive the tidal forces of a Milky Way-like halo, even when we include the baryonic components. And yeah, now my current work is studying this evolution of maximum circular velocities, the concentrations of subhalos, the tidal tracks, and the annihilation in colibri of halos of very, very different masses. So yeah, this is everything. Thank you very much.
Okay, thank you, Alejandra. Do we have questions or comments?
This is a question concerning the selected particle of dark matter. You are basing all your work using the WIMP particles, I assume. Why will it change this work if changing to higher mass particles, for example?
Higher mass, like primordial black holes, or what? How it's higher mass?
For example.
Okay, so I don't know much about primordial black holes, but I think it's a different approach. So, for instance, you would have like whole objects. So in that case, the object would not have. So the thing is that when we use an n-body, the particle mass is much larger than the masses of the particles of the WIMPs that we are assuming. So if in the case of a primordial black hole, it's the other way around, basically. So you would have a very high mass particle there. So stripping, I don't think it makes sense to think about stripping of an object, which is just one object.
Questions?
So concerning the halos of the first part of the talk, what is the internal structure that you are assuming? I guess Navarro, Frank, and White or something like that.
You mean for the host?
For the estimate of the emission in gammas of the Milky Way so any idea of what happened if you change and assume a core in the distribution of dark matter? Will it lower a lot the signals to be expected or not? And something similar for the satellites. So I assume that the satellites whose tidal forces you are studying, they are distributed originally as Navarro, Frank, and White. What happens if they are not?
Okay, so the thing is that for when in my work, I'm studying in particular the dark satellites. The dark satellites are only dark matter. They don't have baryons at all. And according to the cold dark matter scenario, you would expect to have an NFW always. So if you start with an NFW, even if you have a lot of tidal stripping, there's not going to be a core in any case. That's what we find in our works. Yeah, the thing is that if dark matter is not cold, the dark satellites would not be there. Because when you have warmer dark matter models, there's a suppression of the smaller scales in the substructure, and you would not have a very small subhalos. Okay. If you have cores, well, you can see that for the dwarf cases, for instance. It would be basically the same. If you have a core, it's really easy to destroy the subhalo with tidal stripping. Mm-hmm.
Actually, I have a connected question. So in your first part of your talk, when you predict the luminosity of the subhalo population, what do you assume? I mean, how do you model? Is the Navarro white? Is you put a Navarro because I guess the luminosity depends on the profile that you assume, right? And the concentration and everything. Is something that you get out from the simulation after the population, or is something you have to put by hand?
Yeah, well, in that case, we are implicitly assuming an NFW, but we are not, so we don't have the profile in those cases. We only have the parameters like the mass, the concentration, and so on. And then, yeah, assuming the NFW profile, we compute everything. But it's true that it's not completely realistic because we are not taking into account the tidal stripping and so on.
And about the concentration parameter, given that is so critical for the survival of the subhalo, how do you scale or how do you parameterize the C as a function of this, or how do you sample the concentration parameter over your population?
Yes, so this has been studied by Ángeles Molina et al. So they studied the concentration of the subhalos in Via Láctea 2, also in Elvis. But yeah, in this case, we are using the Via Láctea 2 results. And then, yeah, they saw how for different distances to the center, the concentration was different. So when the subhalos were closer, the concentration was larger. And also for the same as for halos, when the mass is larger, also the concentration is larger. And then with that, we are basically using that formula with some scatter that it's also implemented in that paper.
I have a couple more of questions. Is there anybody wants? So also, can you why? I mean, the smaller subhalos. I didn't understand the fundamental reason why the smaller subhalos can be as luminous in gamma rays as the bigger ones. Is it because they are in average closer to us? Or?
Yeah. So it's not. So the annihilation luminosity. So the thing is that the annihilation luminosity is what the subhalo emits itself, and in that case, it's not a larger subhalo would emit more than a smaller one. But the J factor also takes into account the distance to the Earth, and then
so the average they're closer, no?
Yes, exactly.
Okay, I have more questions, but I will ask later. So, but yeah. Anybody else in the room? If not, I will ask. I will invite Wei Wang Kui to ask online if you want.
Hello, can you hear me?
Yes, hello.
Okay, great. Thank you for this nice talk. I have a few questions regarding the identification of the subhalos, especially in the calculation of the concentration of the subhalo, which you have used a lot, right?
I'm not sure I understood the question, sorry.
How do you calculate the concentration for the subhalos?
In which case? In the population or in the tidal stripping?
In the tidal stripping or in because I assume that you have to use the concentration to estimate how the tidal stripping strengths, all those kind of things, right? So for the subhalo, because you identify the subhalo which is lying inside the very dense region, and the concentration estimate for the subhalo is not that current, to my knowledge. Maybe that is only my naive expectation.
The thing is that for tidal stripping, we are just assuming an initial concentration, which is basically because we are assuming an NFW initial density profile, and then you can define easily a concentration of a subhalo, and then you don't worry anymore about the concentration itself.
Ah, okay, okay.
But for the tidal tracks and so on, we are calculating the concentration using the Vmax and Rmax parameters. It's a different definition. So in this case, we don't have the standard values of the mass concentration like from 10 to 50 or something like that. So in this case, we have something like 10 to the 4, 10 to the 5, but it's also a different definition of concentration that it's also more robust for subhalos because Vmax is a more robust parameter compared to the subhalo mass.
Yes, I agree with that. Yeah. Okay. Another question is about the baryons. The people talking about I cannot remember in which conference I was talking with people that are saying that okay, if you have baryons, you have the feedback on the UV background, all those kind of things. The smaller halo, like tend to fall or something that can be evaporated and easily, and it stop them to growing. So I was wondering that whether this will affect what you're saying in the paper. I said in the talk. So I saw you that have the simulation with baryons and try to see that how the subhalo evolve and not evolve the subhalo statics compared to the dark matter only one. It seems more or less agreed with each other. Is that correct?
Okay, the thing is that we should take this, when I say baryons, it's not like hydrodynamical simulation or anything. It's, so it's including the mass distributions of the baryons, but not, it's just including more mass to the host as
Okay.
a stellar disk, a gas disk, and a bulge, but it's not like the subhalo is interacting with this or it's affected by baryonic feedback, supernovae, etc. It's not like that. It's just that we have a larger amount of mass and it's distributed in a more realistic way. But also, thing is that if you go to a cosmological simulation, it's very hard, as I said, because they are limited by the artificial effects and numerical resolution and so on. It's very hard for these small subhalos to survive the tidal forces, the artificial forces in these simulations.
I see. I see. Thank you very much. Good to know that. Yeah.
Okay. Thank you also for your questions. And then if we don't have any more, let's thank Alejandra again for her beautiful talk.